This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today: characteristic of chemical equilibrium. What is chemical equilibrium? That we have already started. Now we will see the characteristic of this chemical equilibrium, then law of chemical equilibrium, equilibrium constant in terms of concentration and in terms of pressure. It can be expressed in two ways. Then activity versus concentration. What is the difference between these two terms? And if time permits, then characteristic of equilibrium constant. Okay. So here we will see different features of chemical equilibrium. So last day we have seen chemical equilibrium as well as physical equilibrium, right? And now details of chemical equilibrium that we have to know. Examples of chemical equilibrium we have seen in the last class with the reaction H2 plus I2, and it is producing 2H. So this reaction, that is based on this example, we have seen the chemical equilibrium. But what is its characteristic that we are discussing now? The system in which the reaction is occurring, that is for which we are uh, talking about the chemical equilibrium, that system must be closed in nature. That means no substance can enter from outside or it can leave from the system. That is not allowed. So if we want to have equilibrium condition, we have to take care of this fact. Even though we don't necessarily see the reactions, that means when equilibrium is reached, it seems as if reaction is stopped, but actually that is not the case. What is happening? Forward reaction, backward reaction, both are occurring simultaneously in same rate. So that is why it seems as if it is constant, that is the reaction is stopped, but actually it is not. So it means that the chemical equilibrium, that is dynamic in nature, it is not static, it is dynamic in nature. The equilibrium can be approached from either direction. So as now we have forward reaction, reverse reaction, both are occurring at the same rate. So we can approach the equilibrium starting from either H2 or I2. Just for example, take this reaction. You can start from hydrogen and iodine mixture. You can reach the equilibrium, and when you have reached the equilibrium, there is a specific concentration of Hi, H2 and I2. But if you want to start from this side, that is you have taken hydrogen iodide, then there is decomposition of hydrogen iodide and it is decomposed to H2 and I2. Now this process will continue and the concentration of Hi will decrease, concentration of H2I2 will increase, and it will go on until that point when the equilibrium concentration of all these three species reached. Okay, so equilibrium can be approached from either direction, and this example with proper diagram that we have seen in the last class, probably that is the last slide in last class, where we have seen that we can move, we can approach the reaction or we can approach the equilibrium, whether you move from right hand side or left hand side, both are possible. The amount of reactants and products do not have to be equal. Don't think that when equilibrium is reached, the amount of product side and reactant side both are we are having same amount, that is same concentration. No, we are not talking about that. We are just talking that there is some fixed concentration of the reactant side and product side species, but not necessarily it has to be equal. After equilibrium is reached, only the amounts of reactants and products, whether it is 3 or 4 products or only one product, irrespective of that. Suppose there are total 5 species. Right hand side 3 species, left hand side 2 species. It may be 3 species, it may be 4 species, different number on both sides, whatever it is. The amount of all the species at equilibrium, it is fixed for all the species. And that is why we can say now we have the equilibrium concentration for all the species. Suppose if I am saying there are total 3 species, so 3 species, just like this example, H2, I2, Hi. So all these 3 species we have some fixed concentration, and this concentration which you are getting at equilibrium, you can call them as equilibrium concentrations. Fine. So their concentration, it is not necessary to be equal, but there is a fixed concentration for all the species involved in the reaction or system. Another characteristic at equilibrium, rate of forward reaction is equal to rate of backward reaction. Then at equilibrium, the observable properties of the system, that is pressure, color, concentration, etc., everything become constant and remain unchanged after that point. That is, once the equilibrium is reached, all these will be fixed. Just try to remember, when we have discussed this example, H2 plus I2, it is a deep violet color solid, and if you keep it in closed container, transparent, you can see some violet vapor, right? Now, once you start the reaction from left hand side, obviously gradually the concentration of iodine will decrease, but it is not that all the iodine will decompose. No, it will decrease. Once equilibrium is reached, now the color intensity of iodine, that will also become fixed. So that is why here it is mentioned color. So I'm just talking about color, not necessarily color. It is also true for the other observable properties like pressure, color, concentration, etc. And once equilibrium is reached, it will change. It will remain unchanged thereafter. State of chemical equilibrium is unaffected by catalyst. Though we do not use catalyst in all reactions, but in some reactions we need to use catalyst. But remember, it has nothing to do with chemical equilibrium. It is completely unaffected by it. Catalyst is basically related to kinetics. That is how fast that you can reach the reaction. And catalyst helps to decrease activation energy. And that is why now the reaction is fast. But that doesn't mean that you will be getting more product. No, that depends on the yield of the reaction. That is at equilibrium condition, how much product concentration is present. That is yield. But how fast you can reach the chemical equilibrium condition, that is all about kinetics. And catalyst is related to that, because when you use catalyst, activation energy is decreased, and as a result the reaction rate is increased. But chemical equilibrium is not affected by this catalyst, because the presence of catalyst equally increase the speed of both the reaction. So ultimately it is the overall effect is nullified. Okay, so even if we use catalyst, it is not affecting chemical equilibrium. State of chemical equilibrium changes with the change in factors like concentration, temperature, pressure. Now this is very important point, that is the last point, because based on this point we will discuss a principle, probably not in today's class, Le-Chatelier principle, which is basically based on this statement, that is the last statement, that once the chemical equilibrium is reached, it is true that observable properties are not changed. That is, naturally these observable properties are fixed, pressure fixed, color fixed, concentration. But suppose forcefully you are doing some change, suddenly you are increasing the pressure, or you are changing the concentration of one of the species, or suppose you are increasing the temperature. Now obviously it will have some effect on the chemical equilibrium. So state of chemical equilibrium changes with the change in factors like this, not necessarily these three, there are some more factors also, and details of this, that is how these factors are affecting chemical equilibrium. Details of this, that will be discussed under Le-Chatelier principle. But obviously state of chemical equilibrium changes if you change these factors, that is externally, forcefully, if we are making some changes, then equilibrium will change. Okay, so these are the characteristics of chemical equilibrium. Now law of chemical equilibrium. So what it says, the mixture of reactants and products that are formed under chemical equilibrium. Just take the example H2 iodine, you are getting HI. Now once the equilibrium is reached, you have mixture of all these three species. That is, you have mixture of iodine, H2, HI. You have all these three species together in the equilibrium condition. So this mixture you can call equilibrium mixture. And concentration of this reactant side species, product side species, when equilibrium state is reached for a reversible reaction, this concentration, this specific concentration, you can call them equilibrium concentration. So it is not the concentration at any time of this reaction, only when the equilibrium is reached, then only you can use the term equilibrium concentration for all the species involved in the reaction whether it is reactants or products. Fine. So two terms: equilibrium mixture, equilibrium concentrations. Now, once we know these two different terms, equilibrium concentration, equilibrium mixture, now some question may arise in your mind. What is the relationship between the concentration of reactants, concentration of products in the equilibrium mixture? It is fine that we have reached the equilibrium, but suppose we want to know what is the relationship specifically between the concentration of reactant side species and product side species. Then another question may be how to determine the equilibrium concentration if you know the initial concentration. So in this case, you have started the reaction from H2 and I2. So you know what amount of H2 you have mixed with iodine. So this is initial concentration that is known to you, and you want to know from these initial concentrations value, you want to now determine equilibrium concentration. Now, is it possible? That is another question. Now, the third question: what factors can be used to alter the composition of an equilibrium mixture? So remember in the last slide, the last statement, what we have seen, that state of equilibrium can be changed by changing the factors like pressure, temperature, etc. That means we can affect equilibrium. Now, by doing so, can we, that is, these factors, can we use in a specific way? Can we use these factors productively to alter the composition of an equilibrium mixture? Suppose from A, I am making it very simple. Suppose from A you are making B. So B is product, A is reactant, right? Now you are asking the question that at equilibrium, suppose from when you have started 10 moles of A, you are getting 8 moles of B, but it is 1:1 reaction. So from 10 moles of A, you should get 10 moles of B only. But if that is happening, that means it is 100%, giving you 100% yield. That is full reaction, but that is not actually, it is one side, it is irreversible reaction. But mostly that we do not consider when you are talking about reversible reaction. So suppose out of 10 moles, only 6 moles we are getting. That means initially it is 10, it is 0. But after some time, or you can say after equilibrium reached, now only out of 10, 5 moles converted to B. That means remaining amount of A is 5 and 5 moles of B produced. So in equilibrium condition, both A and B present, 5 and 5. Now the question we can ask, that if it is true that by changing the outside factors like pressure, temperature, concentration, it is possible to alter the equilibrium. Now if it is true, that means, is it possible for us to change these factors in such a way so that you can increase the yield of B? Increase the yield of B means now from 10 you are getting only 5 moles and 5 moles of A still unreacted. But suppose out of 10 you want to get 8 moles of B. That in that case only 2 moles of A will be remaining. Is it possible? So that is the third question. Now the third question is important in chemical industry. Why it is so? Last question is relevant while choosing conditions for synthesis of industrial chemicals. Why it is so? Industrial chemical means, suppose where H2 is produced in a large scale, ammonia produced in a large scale, calcium oxide produced in a large scale. Now we are producing industrially all these chemicals. What is our motto? What is our purpose? We are trying to make it as large quantity as possible. That is starting from the initial reactants. Our aim is to gain maximum yield of this product. Then only it will be economical. So that is why the last question is very related in this. That is practically when we want to increase the yield, especially in industrial chemicals. Then if this question is very important. So somehow if you can control the factors, then it is possible to increase the yield of product. Okay, so one by one we'll see, we'll try to answer all these questions. But before that, if we want to answer this question, we have to know equilibrium constant. Based on experimental studies of several reversible reactions in 1864, these two persons, they formulated the law of mass action. Fine. What this law says, the law states that at any instant, the rate of chemical reaction at a particular temperature, so temperature is fixed. Under that condition, rate of a chemical reaction is directly proportional to the product of the active masses of the reactants at that instant. Now, what is the meaning of this term active mass? Basically, in older days, you can understand it is 1864. The term active mass is more popular compared to the term concentration. Actually, it is the same thing as concentration. But if you actually want to know the statement of this law as stated by them 1864, in that case they have used the term active mass. So active mass is not a new thing, it is nothing but concentration. So active mass is molar concentration per unit volume of that substance. Okay, so this is the law. Now if this is the law that at any instant temperature fixed, rate of chemical reaction is proportional to product of active masses of reactants. So in short, mathematically how we can express it, rate is proportional to concentration of reactant which is within third bracket to the power x. X means the stoichiometric coefficient of the reactant. So if it is suppose from A moles of capital A, you are getting small b moles of capital B. So in this case, reactant is A and X should be this small a. So I can write rate is proportional to concentration of A to the power small a. So X is the stoichiometric coefficient of the reactant. The square bracket represents active mass or concentration of the reactants, and active mass is nothing but concentration, which you can understand from this N divided by V. So number of moles per unit volume, where volume is in dm cube or liter, and N is the number of moles. Now if it is true, now it is proportional. Okay, so when this proportional, if you remove this proportionality sign, there will be a constant. Now what we'll do, from this law of mass action, now we will try to reach another term which is equilibrium constant. But remember, it is equilibrium constant in terms of concentration, so that is why the subscript we are using Kc. There is another constant which we will use, but that is actually Kp. Okay, later, not now. So here we have taken a reaction where A moles of capital A and B moles of capital B, they are producing C moles of capital C as product, D moles of capital D as another product. Now we will apply the law of mass action for the forward reaction first. So for the forward reaction, small r is the, it means the rate, F is subscript for F means forward. It is proportional to A to the power A, B to the power B. Now if you remove this proportionality sign, there will be a constant Kf, and we are calling it as rate constant. Now the same thing you can do for backward reaction also. But for backward reaction, now we will use a different term which is RB, B for backward, and it is proportional to C to the power C, D to the power D. So as if now you are moving from this side to this side. So these two will be now reactant. So that is why for backward reaction, you have to write it in this way. If you remove the proportionality sign, now you have to place a constant, and we have taken the constant as Kb, and this is called rate constant. Fine. Now up to this point, I hope it is clear. Next step is the reversible reaction that we have considered. Once the equilibrium is reached, we know the condition. Once the equilibrium is reached, rate of forward reaction, Rf, is rate of backward reaction. If we apply this, obviously these two will be now same. Okay, now if we take the ratio Kf divided by Kb, Then right hand side you will get this ratio, and this Kf by Kb, now we are writing it as Kc, and this is known as equilibrium constant, and it is in terms of concentration. So it is important to mention in terms of concentration. Sometimes it is also mentioned as active mass, but mostly we will use concentration because that is a more modern term. We do no longer use the old term active mass, which is basically same as concentration, right? And this equation is known as law of mass action. So here it is mentioned, see, concentration was called active mass in older days. So next, some more information we have to know, that that is this equation that you are seeing here, how you can state it. You can state it in this way, and you can also call it law of chemical equilibrium or equilibrium law. And how we can state this equation, it is like this: at a given temperature, the product of concentrations of the reaction products raised to the respective stoichiometric coefficient. That means we are talking about these two, C to the power C, D to the power D, in the balanced chemical equation. So this equation that we have taken, though it is general, you can't understand what are the actual species involved, but remember, this should be balanced. When you will actually use any particular reaction, remember, don't forget to balance it, and then you put in this equation. So respective stoichiometric coefficient in the balanced chemical equation and divided by the product of concentration of the reactants raised to their individual stoichiometric coefficient. Same thing. Now A to the power A, B to the power B, but that is in denominator. And this ratio will have a constant value, which is, and this is this statement, total statement, which is basically explanation of this equation. You can call it law of chemical equilibrium or equilibrium law. But Kc is known as equilibrium constant in terms of concentration. So now we will try to solve this problem, what it is saying. In a chemical reaction where reactant side we have A plus 2B, so you can consider it as if it is already balanced. Then K, equilibrium constant, equilibrium sign is there. Product side you are getting 2C plus D. Here some informations are given related to concentration of B, concentration of A. It is saying that initial concentration of B, initial concentration means when the reaction is not started at all. Initial concentration of B is 1.5 times of the initial concentration of A. But when equilibrium is reached, equilibrium concentration of A and B both are equal. So now you have to separate information. It is saying once, that is before reaction started, concentration of B greater than concentration of A by 1.5 times. But once equilibrium is reached, concentration of A and B both are same. So from this information, you have to find out the equilibrium constant K for this aforesaid, that is previously mentioned, chemical reaction. We have 4 different values: 4, 16, 1 by 4 and 1. So what you will do, you will write this equation and you have to just assume any X or A, whatever, as if it is the initial concentration. So what we will do, see, we have written this reaction and initial concentration as it is mentioned 1.5 times. So two things you can do. Here it is written as, that is for to make the calculation simple, here it is written in this way, 2 and 3. So you can see when T is 0, that means reaction is not started at all. A concentration is as if 2 moles, this is 3 moles. That means 3 is 1.5 times of 2. Now you can say, why I will not write it here 1 and this is 1.5. Basically it is actually same thing. You can also do so, but if you consider a whole number, it will help you. So whatever calculation now I will show in terms of 2 and 3, the same thing you can also do considering 1 and 1.5. Not just 1 and 1.5, you can also consider it like this. Suppose if it is, I'm saying, instead of 1 you are writing A and this is 1.5 A, because we don't know what is the actual amount. We just know the ratio, and this is 1 is to 1.5. But you can consider it like this, or you can simply, if you want to make the calculation simpler, you can simply consider 2 and 3. So here we are considering 2 and 3, but remember you can also do so. That is also fine. It is not something you are doing wrong. So A 1.5A, or you can write 2 or 3. Important point is the ratio should be 1.5. So 3 by 2 is 1.5. Then 1.5 A by A, that is also 1.5, or simply if it is 1.5 by 1, that is also 1. Okay. So 2 and 3, that is the ratio is important. Now once equilibrium is reached, look at this coefficient of A and B. The coefficient of A and B is basically 1 and 2. So there is 1, there is 2. That means out of 2 moles, if X moles consumed at equilibrium, obviously 2x moles of B will be consumed, because the ratio of stoichiometry is 1:2. So if you are writing 2 minus x, because x moles of A suppose consumed at equilibrium, obviously you have to write 2x. Don't write x, otherwise it will be wrong. So that is why it is important for us to balance the equation. Suppose this reaction is not balanced, and then you are doing the calculation, it will be wrong. So 2 minus x, concentration of A at equilibrium, and for B it is 3 minus 2x. And this side, right hand side, initially it is 0, 0, because product is not yet produced. But now again compare the coefficient. With respect to A, C is double. That means if X is consumed, obviously 2x of C will be produced. With respect to A, D is 1:1. So if X moles of A consumed, X moles of D will be produced. You can also consider from the point of view of B, that is 2B, 2C. This is also 1:1. So when 2X is consumed for B, obviously 2X of C will be produced. Similarly, what about 2D, 2B and D? 2B and D, 2:1. So when 2x moles of B consumed, you will get 1 mole of D. So whether you consider from the point of view of A or 2B, you will basically reach the same conclusion. So this is the first information, 1.5 times. Now it is also saying that equilibrium concentration of A and B, they are equal. That means these two at equilibrium equal. So you are getting another equation. Now from that equation, you can easily get the value of x. And once you know the value of x, you can find out the value of equilibrium constant. So given 3 minus 2x equal to 2 minus x. So this is the concentration of B at equilibrium, concentration of A at equilibrium. From this equation, you will find the value of x as if it is 1. Now Kc, if I write it elaborately, it is basically C to the power 2, because coefficient is 2. Then D, coefficient is 1. A, coefficient 1. B, coefficient 2. So now you know the value of C at equilibrium. It is 2 into 1. So 2 into 1, 2 to the power 2. D, concentration X, which is directly 1. Concentration of directly 1. And here you will get concentration of B. Sorry, concentration of A is 2 minus 1, which is basically 1. Concentration of B, 3 minus 2 into 1. That is also giving you 1. So we will put here 1 square. So see, same thing, and you will get 4. So this is the correct option. Okay, so in this way we will solve this type of problem. So in equilibrium, that is, sorry, it is wrongly mentioned. It is equilibrium chapter. Okay. So while solving problem like this, or very that are designed in this way, where you have to find Kc, then mostly we'll see you have to write this equation. You at equal to 0, you have to assume some values. Then at equilibrium, you have to again write the concentration. So same thing you have to do for this type of for solution of this type of problem. Equilibrium constant at 298 Kelvin. Temperature fixed, we know. We then only we can give the definition of Kc. For a reaction A plus B producing C plus D is 100. So very high value. If the initial concentration of all the 4 species were 1 molar each, that means initial concentration of all 4 species. See, as we know, you can reach equilibrium whether you start from left hand side or right hand side. It doesn't matter. And in this case, you can see initially you have started 1 mole for all, right? Then if it is so, what will be the equilibrium concentration of D on D in moles per liter? So we will write the equation. That is the first thing we have to do. Initially, that is T equal to 0, all are 1. It is not that only reactant side 1, all 4 are 1. Once T equilibrium is reached. Now suppose out of 1, only X amount consumed. And A and B, as it is balanced reaction, obviously by default you can consider it balanced. Otherwise it will be mentioned clearly in the question. So 1 minus X, suppose X moles of A only consumed. Obviously in B also X moles of will be consumed because it is 1:1. Now in the right hand side product, already some amount of C is there, but as X moles of A and B consumed, so C now will be having concentration 1 plus X. So it will increase. Initially already there is 1, now it will be 1 plus X. For D also it is 1 plus. Now we will write the value of equilibrium constant, and here it is concentration of C, D, A. Stoichiometric coefficient all are 1. So we will write 1 plus X 2 times. One minus X 2 times, which is 1 plus X. Right? So now what we'll do, it is only asking the equilibrium concentration of D in this case. So somehow if we know what is the value of X, then you can find concentration of D, because concentration of D is now this value is 100. So both sides if you take root, you will get, it will be simplified 10. That means 1 plus X. Now it is 11X 9. So X is 9 divided by 11, and this value is 0.818. That means if X is 0.818, it should be, so correct answer should be second option. Okay, so in this way we'll solve this problem. So Kc is done. Now equilibrium constant in terms of pressure. So sometimes it may happen that a particular reaction, some gaseous species are involved. So in that case, rather than expressing it in terms of Kc, that is in terms of concentration of the species involved, you can also do it in terms of pressure. Okay, so in terms of in place of concentration, now we will write pressure. So how we can do it and when we'll do it? If the reactants and products of any reaction, they are in gas phase, then the equilibrium constant can be expressed in terms of partial pressure of given mixture. So what is partial pressure? That we have seen in states of matter chapter. So suppose you have mixture of 2 to 3 gases, then a particular gas, its pressure will be mole fraction of that particular gas multiplied by total pressure. So in this way we can find partial pressure. So we can express it in terms of partial pressure, obviously temperature fixed for all the species involved. So same thing you will now you will just have to change the concentration terms in terms of pressure. That is the difference. Now how we will reach that? For that you have to know, you have to use this ideal gas equation, which is PV equal to nRT. That means P equal to N by V RT. Now N by V is nothing but concentration, number of moles divided by V. that is number of moles per unit volume. So N is number of moles, P pressure, V volumes, R is universal gas constant. And active mass, remember active mass, which is nothing but molar concentration, that is actually N by V, right? Now right hand side, if as in the here it is mentioned given temperature, that means T is fixed, R we know it is already constant, that means R constant, T constant, so pressure should be proportional to N by V, that means pressure is proportional to active mass, or you can say pressure is proportional to, because this is constant, right? So pressure is proportional to active mass, or pressure is proportional to concentration of the gas. Okay, so that is why it is written gas, any gas within third bracket, that means it is a concentration or active mass of the gas, whatever way you express. Now I will use the same equation that we have already used, so that you can compare both the equations together. So in this case, we know that Kc, how we express it. In case of Kc, we express it like this: C to the power C, then D to the power D, A to the power A, B to the power B. But now we are not doing so, because now instead of writing concentration C, as concentration is proportional to pressure, it is proportional to concentration. So that is why in terms of C, now we can express it in terms of P. So here you see P of C, that means pressure of the gas C. And remember, all these are now gas. That is why we are using it. So this is the partial pressure of C, and raised to the power, that is its stoichiometric coefficient, which is small c. Then partial pressure of product D raised to the power small d. So in this way, in these four positions, you will write the pressure terms, and also this subscript will be changing. So here PA, PB, PC, PD, small p obviously, because it is partial pressures of all these four gases respectively. Okay, so this is the difference. Equilibrium constant in terms of concentration is Kc, and for gaseous substances it will be in terms of Kp. Now related to Kp, we will discuss this problem. Suppose you have two solids, one is solid A, another one is solid D. In bracket it is mentioned S, that is the physical state. Now they are dissociating as follows. So solid A dissociating in B physical state G, that means gaseous product, another gaseous product, and its Kp value, Kp1 basically, because we are using two separate equations. So Kp1 is X atmosphere square. Now you may be thinking that Kp, Kc, whether they have units or not, but regarding that I have separate discussion, because regarding unit, different ways it can be expressed. Sometimes units are present, sometimes units are not present. So what to do in detail we'll see separate. Right now just focus on the problem, not on the units. So Kp1 value is X atmosphere square, and for the second reaction, same type of reaction. Here also from a solid you are getting two different product gases, capital C, capital E. Here Kp2 value is given Y atmosphere square. The total pressure when both the solids dissociate simultaneously, then what will be the total pressure? That means total pressure, now you have to consider the pressure of B, C and E. And one important point that is interesting here, this product is common for both. Okay, we have some options in terms of X and Y. So first write these two equations. So suppose here we have solid left hand side, and we are talking about Kp values. So you don't have to bother about A, because it is not gas. So its term will not be present in the expression of Kp. Only gaseous substances expression will be there in Kp. Okay, so ignore these two. So from A you are getting gas B, whose pressure is basically P1, and for C that is also P1 because both are in 1 moles produced, 1 mole 1 mole. Stoichiometric coefficient ratio is 1:1. Similarly from D, now why it is P1 plus T2? Basically C is common in both the reactions. This is equation 1, this is equation 2. In equation 2 from D, 1 mole D, you are getting 1 mole C, 1 mole E. So here basically the partial pressure of C and E, P2, P2. But as you also have to consider the partial pressure of C, which is generating from equation 1. So that is why we have to write in this way, that is P1 plus P2. Now how you will express Kp1? It is a partial pressure of B raised to the power 1, partial pressure of C raised to the power 1. In denominator there is nothing because A is solid. Now in the place of Pb you will write P1, in place of Pc you will write P1 plus P2, and Kp value is X, that is already given. Same way in place of Pc, as you have written here, this is actually Pc. Here also same Pc, same partial pressure, because now both are occurring simultaneously, and partial pressure of E is P2. Fine. So up to this point it is okay. Now if you add these two equations, so left hand side you have X and Y, suppose you are adding these two. So when you are adding these two terms are also added in the right hand side. That means P1 plus P2, then P1 plus P2. So this part is common. So if you take P1 plus P2 common, you will be left with P1 plus P2. Basically these two are same, so there will be a square. So that is why directly here it is written as square. But it is asking the total pressure when both the solids dissociate simultaneously. What is the total pressure? Now total pressure is basically P1 and P2. So P1 and P2, that is, sorry, I'm not talking about total pressure. The value of P1, P2, when it is in square, it is X plus Y. So if you remove the square, both sides, if we take root, it will be P1 plus P2. This value is root over X plus Y. Now you have to calculate the total pressure. So total pressure is PT, subscript PT. Now when you are talking about total pressure, you have total 3 species. You have species C, species B, species A. Total 3 species. B, C is common, and E. So total 3 species. Now PC and PB. The PC total pressure is basically P1 plus P2. This is the final pressure for PC. So this term we have written for PC. This term we have written for PB. This term we have written for PE. Okay. So P1 plus P2 coming 2 times. That means it is 2 into P1 plus P2. But you have already calculated P1 plus P2, which is basically root over X plus Y. So that is what is written 2 into root over X plus Y, and that is actually PT, total pressure. So this should be the correct option. Consider the reaction nitrogen gaseous 1 mole, that is 1:3 nitrogen hydrogen ratio, 3 hydrogen gaseous. Product side we are getting 2 moles of ammonia. This is balanced equation. This is also gaseous. Equilibrium constant of the above reaction is Kp. Now if pure ammonia is left to dissociate, so as if we are starting from this side, that is also possible. So if you have started the reaction by taking some ammonia and you are leaving it to dissociate to nitrogen and hydrogen, then the partial pressure of ammonia at equilibrium is given by any of these 4 options. And in the options, if you look carefully, you will see Kp value is present directly in all of them, and there is also the value of capital P. So capital P is basically the total pressure, and here you have to consider this assumption because that is already mentioned in the question, and that is important assumption. If you do not apply this, you will not reach correct answer. It is saying to assume that partial pressure of ammonia is very less compared to the total pressure at equilibrium, right? So this assumption we have to apply. So we will start the reaction like this. We are starting from this side, just reverse the reaction. Now for this reaction, if that is equilibrium constant of this above reaction is Kp. So for this reaction, it is expressed as Kp. So when you have reversed this, now it will also be reversed. Okay, so see the equilibrium constant for this new reaction, which is nothing but the reverse of the old reaction. So now this will also be reversed 1 by Kp. Now how to know that when a equation that we'll also see in detail later. Right now just focus on this fact that if you reverse an equation, the corresponding equilibrium constant that will also be reversed 1 by Kp. If it is Kc, then also it is 1 by Kc. So 1 by Kp, how you can express it, even if you do not write it, it is okay. So this is basically the equilibrium constant for this reverse reaction or backward reaction. So 1 by Kp, now partial pressure of nitrogen to the power 1, partial pressure of hydrogen to the power 3, because that is the stoichiometric coefficient, divided by partial pressure of ammonia, starting material, to the power 2, because this is the coefficient, right? So until this point, it is okay. Now we will apply the assumption. It is saying that total pressure, which you can also write as if it is P, simply P. Total pressure is partial pressure of all these three species, because once you reached equilibrium, basically you have all these three species together. Now compared to total pressure, as partial pressure of ammonia is very less, so as if it is equal to partial pressure of nitrogen and hydrogen only, we are ignoring this part. So we are not taking this part, it is removed because of this assumption. Now if it is so, next what changes we can write in this expression of 1 by Kp, that we have to see. So same question. So now partial pressure of nitrogen, which is basically this value, remember. So individually we will now find out what is the partial pressure of nitrogen, what is the partial pressure of hydrogen, because once you know these two values, you can put it here, and from this you can find out the pressure of ammonia, because that is actually you have to find. In the question it is mentioned partial pressure of ammonia at equilibrium, find out. And in this expression there will be Kp and there will be that is capital P. That means these two now you will be expressing in terms of capital P, which is basically the total pressure, right? So partial pressure of nitrogen, that is actually 1/4 of P. Now why it is so? Remember what is the ratio of N2? It is 1, it is 3H2. That means for 1 mole N2, it is 3 moles. So total number of moles, as if it is 1:3. That is the ratio is 1:3. I am not saying total number of moles 1 mole and 3 moles, but ratio is important here. Actual value not important. And mole fraction will be total number. Even if you write it as x and 3x, that also doesn't matter, because total number of moles 4x, x plus 3x, and number of moles for nitrogen x. So whether you consider x 3s or 1 3, you will always get 1/4. So don't make it unnecessarily complicated. Simply write 1 and 3, and this is the mole fraction of nitrogen. So mole fraction into total pressure, that will give you partial pressure of any species. So for hydrogen similarly, the mole fraction is 3/4, because total number of moles for hydrogen is 3 or 3x, and total moles x plus 3x, that is 4x. So x cancel, it is 3/4. So mole fraction of hydrogen, total pressure. Now the same expression in the previous slide we will use here. So in place of Pn2, now we will write 1/4P. In place of pH2, we will write 3/4P. and this is as it is. Don't change it, because after all you have to find P ammonia, right? Now, one by bring this term here in the left hand side. So if you do so, in the right hand side, what are the changes you are getting? Kp will be here, right? Then P by 4, then 3P by 4. Basically, it is 3 to the power 3, 4 to the power 3, and P to the power 3, right? Now, this side, if we take root, then only you will get P ammonia. So that we have to find basically. So this side, what we are getting, if you, okay, Kp. So Kp will be as it is. Then pressure terms, it is P 3 and 1. That means 1 plus 3. So it is P to the power 4. But when you will take root, let me write it in the root also. So P to the power, it is actually 4. Then 3 to the power 3. And it is basically 4 to the power 4. Okay. So ultimately you will be, you will get Kp P square, then 3 to the power 3. You will get 3 by 2, and there will be 60. So ultimately you will get this term, or if I arrange it, it will be 3 by 2. Just I'm trying to match with the options. Then it is P square, and then so 3 to the power 3, if you take root, it will be 3 by 2, as if it is 3 into half. So that is why I have written 3 to the power 3 by 2. And 4 to the power 4, it is, if you take root, it will be 4 to the power 2, which is 16. So it is matching with which option? Last option, right? So it is matching with the last option. 3 to the power 3 by 2, Kp, and then P square. So this is the partial pressure of ammonia in terms of capital P and Kp value. Fine. Activity versus concentration. Now, if we start this, we will not be able to finish it. Still, to some extent, we can do. So, activity and concentration, this is actually not related to the previous discussion. It is completely new, because sometimes you can find the term activity mentioned in textbook. Mostly it is concentration we use, but activity also can be mentioned in sometimes. What is the difference between activity and concentration? That we should have clear idea about it, right? So activity is mainly expressed in terms of small a. So just like we say, suppose I am saying concentration of X. Similarly, you can say activity of X. So activity of X means it will be like as if A subscript X. Activity of Y, A subscript Y. So activity of a substance. What is the difference with concentration? It is basically the effective concentration of that substance in the reaction mixture. Now, what is effective concentration? Suppose the species is present, only that species. It is lone species. There is no other species. So X, there is only X. It is not mixed with Y or Z. So when this is the condition, you can use the term concentration. It is simple. But suppose you have mixture of some species. You have X, it is mixed with another substance Y, it is also mixed with Z, and also there is some substance, solvent. They are mixed in solvent. So now it is as if present in reaction mixture. Now what happens when X is present in lone state and when it is present with some other species? Obviously its behavior is different. Now ideally we cannot use the term concentration. That is, I'm talking about ideal case. Now you should use the term activity. So activity takes into account the non-ideality of the condition, non-ideality of the reaction mixture. Because when you have reaction mixture, There will be some solvent-solvent interaction. Suppose all these three species present in water. So there will be interaction between two water molecules. Then there will be interaction between water molecule and solute. Then there will be interaction between solute and solute. Even if you do not consider Y and Z, suppose just X is present in water, then also it is applicable. Interaction between two X, interaction between two H2O, interaction between X and H2O, everything possible. And that is creating some situation which is non-ideal situation. So this interaction that will hamper their individual features. So when X is present, it is lonely, then it will behave in such a way which is ideal. But when it is in mixture with some other species, obviously its behavior will be different, and that we are calling non-ideality, and we should use the term activity. So activity can be used in place of concentration to describe the behavior of real situation. So when it is real situation, you use activity. When it is ideal situation, you can use C. But what we do, generally we do not use activity, because the solution that we deal with, it is mostly very dilute solution. So you can expect when it is very dilute solution, here also X is present in water as if solvent is water. Now as it is very dilute solution, individual molecules, they are far from each other. So interaction will be now less and less. So that is the reason for very dilute solution, activities of the substance, it can closely approach the formal concentration. Fine. And mostly we deal with very dilute solution. So even if you do not use activity, it is fine. But we should know what is the difference between these two terms. Okay, details we'll discuss in the next class. We are at the end of the session. Thank you for listening.